Transformer ratings are specified by the kilowatt and also the kV of the transformer, and power engineers should be well aware of these various ratings. So today we will cover about the power rating of the transformer, how transformers are specified in terms of the power delivered by the power transformer. I am Ramachandran. I am a specialist in transformers. When the transformers were developed in the beginning, the transformer power rating was specified in terms of the kilowatt or the horsepower delivered by the transformer. This was as usual with all other electrical equipments like motors or generators. But by around 1920, engineers understood that transformer performance or characteristics are more defined by the kVA delivered and not by the kilowatt of the power handled by the transformer. So by around 1927, when the British Standard 171 was first issued, the transformer rating was in terms of kVA or MVA of the transformer. And this was continued till 1970, when British Standard was revised and the transformer rating was specified by terms of the input to the transformer, not by output. So when you say a 10 MVA transformer, it means the transformer can take on the input side 10 MVA and slightly less will be delivered from the output side. And when we take the latest IE 676-1, that is the standard for power transformers in IEC, the latest edition was in 1911. As per this, the transformer ratings are divided by the R10 series of ISO 3 standard, where the preferred numbers are given. As per this IEC, from between 1 to 20 MVA, the ratings are specified by R10 series. It means that from 1 to 10 MVA, the whole range will be divided into 10 ratings. Each is a multiple of 1.25. This is based on the R10 series, means the 10th root of 10, that is each will be a multiple of 1.26. But many utilities find this is too much variation, and so they prefer to go by the R5 series. That means 1 to 10 MVA is divided into only 5 ratings, and each rating is a multiplier of 5th root of 10, that is 1.58. So the ratings will be 1, 1.6, 2.5, like that. It goes like that. When we look into the rating of the transformer, the power ratings, when it goes up, the cost or the weight of the transformer will not change linearly as the rating goes up. It will be varying as the rating raised to 0.75. That means if the transformer rating doubles, say from 10 MVA to 20 MVA, 20 MVA transformer will not weigh double the weight of 10, or it will not cost twice the 10 MVA transformer cost. It will be only 2 raised to 0.75, that means only by 1.7 times. This means that always when your total load is decided, always better to go by as high rating as possible. But the rating is also to be limited by the breaker that has to be used on the secondary side. So if the rating, if the breaker must be able to rupture the current given by the transformer with its impedance. So the selection of the transformer, the rating is decided like this. Suppose think of the total connected load to the transformer, and then also you provide a margin for the extra demand that may come in the coming years. So this may be 10 to 25% more, and this is then multiplied by the demand factor and diversity factor. Demand factor is defined as the maximum peak demand that may come on the system divided by the total connected load. This will be always less than 1. Diversity factor means the total peak demand that may come on the transformer divided by the individual peak of each feeder or each load, that sum of that also will be less than 1. So these 3 factors are multiplied to find out the total rating of the transformer, that is total connected load, expected increase in load factor 10 to 25%, then the demand factor multiplied by diversity factor, that decides the rating of the transformer. As per the American standard IEEE 5712, the rating of the transformer is always the output, that is American standard has not changed to the input rating as done in case of IEC standard from 1970 onwards. The rating in as per this American standard also has a definition that the rating of the transformer is supposed to say ONAN and ONF depending on the cooling. If it is a 10 MVA by 12.5 MVA, 10 MVA delivery at ONN, 12.5 at ONF. As per IEC standard, the rating is, base rating is 12.5, that is highest rating, and all the parameters, that is the losses, impedance, are defined based on the maximum rating. But as per American standard, these ratings, base rating is the lower rating, that is the ONN rating is the base rating, and the losses, impedance and other parameters are always defined based on the lowest rating. And the transformer is also sometimes required to meet the harmonic loading. So naturally there are 2 ways of handling it. One is the power rating is reduced depending on the extent of harmonic loading. Also there are what is called K-rated transformer, where extra margin is built into the transformer to take care of this extra heating from the harmonic loading. So this K-rated transformer, if it is a K17, it means it is capable of taking 28% of the base current of harmonic current, still it will be able to deliver the rated power. And also the rating is also depending on the type of use. For example, in a power station, if a generator is say 100 megawatt, then the generator transformer rating should be around 125 to take care of the power factor and also the drop, kVA drop in the transformer. And in case of solar and wind transformer, the peak will be only for a small duration. So the rating of the transformer can be on 20% less for solar compared to the peak, and for about 10% down from for the wind transformer. And the maximum rating, power rating, also depends on the temperature rise, maximum permissible temperature rise. For example, when as per IEC standard, the rated power when delivered at the annual average ambient temperature of 20 degrees centigrade, the maximum temperature rise will be top oil 60, winding 65, and hot spot will be 78 degrees centigrade. And if any of these parameters, that is ambient of 20, 30 and 40, is exceeded at any particular place, then the maximum winding and oil temperature are reduced to that extent to take care, so that the hot spot of the absolute hot spot in the winding will not exceed the maximum as per standard. Similarly, the rating is also, power rating is to be reduced when the transformer is put up at high altitude due to the lower density of the air prevalent at high altitude. The extent of reduction is up to more than 1000 meters. For every 100 meters rise above 100 meter altitude, the temperature rises or reduced by 1 degree centigrade. And if it is that is in case of natural air cooled transformers, and in case of forced air cooling, for every 250 meter increase from the 100 meter altitude, the temperature rises is reduced by 1 degree Kelvin, so that to that extent the power should be reduced, so that temperature rise is within limits. So we have seen what is meant by the power rating of a transformer, its significance, and how it is to be adjusted for various ambient conditions in terms of temperature and also altitude and the type of loading like harmonics, how the power rating is to be revised or downgraded so that the total expected life from the transformer will be maintained.